for this week's lab, it's very similar to last week's lab, where you filled out this table and you had to go through um, the various situations via the simulation here on the right side. This simulation you could use for the inelastic, or sorry, the elastic experiment as well. I just find that the one that I gave you last time, I think it was just this one, is a little bit more user friendly and less prone for you to make mistakes. This one, I'm just kind of pumping it up a little bit so that you guys can get a feel for what's going on in the inelastic situation. Okay, so feel free to experiment with any of the other simulations. But for this one, you're going to, I would suggest that you listen to the YouTube video. I think it's very similar to what was said last week. Here's the simulation, which is on the right, and you are going to select the sticking process of this. So you want this to say stick, so that these things stick to one another. And you don't want the reflecting borders up. So you're just going to want to see them bounce one time and then go off into, you want us to see them go off the screen. So in terms of the appropriate boxes, I would say to check the velocity vector, because in the drawings, I'm going to ask you to draw the direction of the momentum vector. Like I said, to check the velocity, I want you to uncheck the velocity vectors. Probably keep the momentum vector checked. Center of mass isn't really all that important. Kinetic energy, I would keep that value up there because you definitely want to see what's going on before and after. You're going to want to calculate it too. And then you might want to keep the values up there just to keep you straight. One thing to note is that the values here are an absolute value scenario, but when we start plugging them in, hopefully you recognize that if something has a velocity vector value of negative, that means it's basically going to the left or opposite of something that is positive. So most of the time to the left is negative. You can make to the right negative, but then to the left would be positive. So just be mindful of that. Let's see, I'll probably keep this path on. Let's see, I think it just kind of gives a little trail of what's going on. Yeah, just this little thing here. And let's reset it. And I like to set this as slow. So let's see what we can do here. What else? So you may need to reposition these balls. If these balls are, set up such they're not lined up with one another, you're going to want them to line up with one another such that the Y position is 0, right? So in this case, it looks like it's not 0. So we want that to be positioned its Y value right in line with this so that they can collide. Okay, so let's just say that this one I changed to 1.5 in mass. So it'll be 3 times as large as the one to the right. I position it at some X position, which is really important. And the Y is 0, which is very important. The velocity in the X direction is strictly positive 0.5. It has no component in the Y direction, its velocity. You can see what the component in the X direction is, and obviously in the Y direction, it would be 0. Okay, so for the second one, let's just say I change this to 2 kilograms. And let's just say that its velocity, the pink one, let's just say I made up something that was also negative. So let's just say it was, its position is 0.5. So it just means that it is Well, let's change that. Be positioned somewhere else. And let's say it's 1.32. But let's let the velocity vectors go in the same direction. So let's just say that this one is 1.5 meters per second. Now, in this situation, you won't see them collide on the screen because this one is going to be going 3 times faster than this one over here on the left. So if that's the case, I would suggest that you just reposition them, right? All we're looking for is some collision. All right, so we reposition. You can see what the velocity vectors look like. Right? We're going to want that Y position to be 0 again, and if it doesn't, or you can't click it into that position, you just click right here and fix it at 0, and you should be good. You don't want there to be a Y component for the velocity vector. Otherwise, instead of going just strictly horizontal, it'll have some vertical component. And if they do click, if they do collide, then it'll be sort of a glancing blow, and that's not really what we want. We want to stay in a one-dimensional sense for this experiment. Okay. Also, I think I say here in the directions, so you're going to draw the before and after collisions. So what you're going to want to do, and you do not want to draw exactly as you see in the in this picture here. So you're going to want to scale it down. If you know that this velocity vector is 3 times as long, then you're going to just scale it down. So just make sure that this longer one, when you draw it, is roughly about 3 times the length of this one over here. Okay, so if you do something like this and draw them just like that, I'm not going to know which one is which because they overlap so much. So just be mindful of that. Those are going to be points of emphasis on your for your lab. So let's just say I position this one just a little bit further down here. Again, got to repeat myself on this. Its Y position is at 0. So, and its velocity in the Y direction is also 0. So let's go ahead and send it and see if I can get these two to collide before it reaches the end of the screen. Okay, so it looks like they are. Now, before I do anything, before I get any measurements, you should already know what the velocity, the kinetic energy of the system is. So it would be this amount here, which comes from the formula 1/2 mv squared. That's kinetic energy for a single piece. So you should be able to calculate that. And you're going to add that to another 1/2 mv squared. The velocities obviously are different. So the sum of those two give us the total kinetic energy for the system. And now remember, I'm going to continue this on. This is an inelastic collision, so you should see this sticking, right? So they stick together, but notice now I've lost some kinetic energy. I've lost about 0.43 joules. I believe before it was 2.44. So I lost that collision. I get these things to stick on the screen. I let it play out and it runs off the screen. And that's fine. Okay, it leaves this little trail. So if I return it back, you can get them positioned as whatever the default is. I'm not sure what the default position is, but you can experiment with this. All right. If you're curious, if you want to see what happens with this thing slipping, let's see, we get a collision here. I don't think there's going to be any slip in here because they are in the same direction. So basically, if they're in the same X direction, there should not be any slipping. What typically happens is for a slipping process, which we're not going to do, you'll see something maybe that looks, let's see if I can get this position a different way. Let's see if I can get this Y for this one to be up a little bit. So I'll change that to, let's say, 0.5. Right, so these, And so I think when you send it, I'll make it go a little faster. You get this kind of glancing glow. That path thing was a little bit annoying to me, so I'm going to take it off. As opposed to this sticking, so you may see something that looks like this. Okay. But that's not anything that we're dealing with right now for this experiment. We're just dealing with the one-dimensional situation. Remember, Y position and Y velocity should be both zeros or both the same. Probably easier just to make them both zeros. Reposition. If you can't get it to click in that one position, then you'll just need to change it by clicking on it. And again, you're going to want collision to occur, hopefully on the screen. All right. All right. And then again, you're going to draw the pictures, and then you should do a sample calculation for the fifth trial down here and fill in as necessary. All right. And this thing continues to move off to infinity. All right. So that is my spiel for the